Okay, we're going to continue on here, chapter 2, hopefully wrap it up, and then maybe we'll get into some chapter 3. So we last time talked about, again, significant figures, how to use significant figures in calculations. So we want to just review a couple of things that we talked about. Remember that when we do multiply or divide, it is the sig figs that we're looking at, and your answer should have the same number of sig figs as the one with the smallest number of sig figs. So whichever sort of value in your calculation has the smallest number of sig figs, that is really how many significant figures your answer should have. When we add and subtract, we do a little bit different. We actually look at decimal places. And once again, it is the smallest. So the lowest number of decimal places or smallest number of decimal places is how many decimal places that your answer should have. Again, not how many significant figures necessarily, but how many decimal places you should have. And remember, if you do some type of combination of these different sort of processes, you want to keep track of your significant figures. You don't really want to round to sort of the very end, but you do want to keep track of it. And it really does come down to keeping track of it, and really sort of the last sort of mathematical step that you do oftentimes will determine sort of how far you should take your answer to. We then talked about towards the end there, density, right? And density is mass divided by volume. Common units of density, grams per milliliter or grams per cubic centimeter. And again, remember that 1 milliliter is the same as a cubic centimeter. We do get oftentimes this sort of volume a couple of different ways. We could just take obviously a volume reading. We could do volume by displacement like we did in the lab and we talked about in the lecture last time. Remember, volume by displacement, you can really find the volume of the object by taking the final volume minus the initial volume. And this is a situation where basically you displace some water or something like that. You put a solid in there, the liquid level will rise. And again, that sort of difference there in the volume is really the volume of the object in that particular case. Obviously, we talked about this and done a number of times in a couple of labs that we did to get a volume such as this. You could do some length times width times height measurements. And again, if these are all in our centimeters, that is how we're going to get to our volume, which is centimeters cubed. Question on that stuff that we talked about last time. Okay, so I think we have one more sort of density example to roll with here, so we'll do that one. Student needs 150 cubic centimeters of salt in an experiment. The density of the salt is 2.16 grams per cubic centimeter. How many 1 pound boxes do they need? Remember a conversion that you need to know. 1 pound is 453.6. Okay, let's take a look. So again, here we're dealing with density. So our formula, density is equal to mass divided by volume. In this particular case, we have 150 cubic centimeters, and that is a volume. We have the density given to us, which is 2.16 grams per cubic centimeter. So if you weren't sure, we definitely have density, we have volume given to us. So mass seems like a very good thing to solve for. In this case, if we rearrange it, remember that mass will equal volume times density. We could actually use sort of the density here as sort of conversion factor. We could use it such as 2.16 grams over 1 cubic centimeter. We also could flip it around and use it up on top, cubic centimeter over 2.16 grams. As we will talk about next, when we do problems in chemistry, they do want you to kind of show your work a lot of times through a process known as dimensional analysis, which we'll talk about in just a bit here. And that's really just showing the units and using conversion factor to show sort of the units canceling out. So in this case, we could start with our 150 cubic centimeters. Basically, when we do this type of calculation, opposites cancel each other out. So although it's not really a fraction here, our cubic centimeters are up on top. So the opposite location here would have the cubic centimeters on the bottom, and 2.16 grams per cubic centimeter. The units here will cancel, and that's because we're basically dividing cubic centimeters by itself. So it becomes 1. And if we multiply that out, we do end up with 324 grams, as this is the only unit that is still left. We're basically multiplying across the top there, and you would come back and divide by anything that's on the bottom, but everything on the bottom is 1, so not much to divide by in this particular case. In this case, though, sig fig wise, I should probably end up with what number? Well, we're multiplying, right? So this has how many significant figures? 2, as there is no decimal the way this is written. This guy has 3, which means my answer actually should have 2, right? And that would take me to 320 grams of salt would be needed. And to answer the question, you would need just 1 box, right? Since 1 box is 453.6 grams, you should have enough with some left over in that case. Any questions on that? So this sort of way of showing the calculations, again, we're going to kind of lead into that next here, is really how they want you to show a majority of your calculations as you go through with the units, kind of using things as conversion factors and showing those things canceling out. So they expect you to kind of show most of your calculations in this fashion. Before we get officially into that, any questions there on density? Okay. Okay, give me a sec. We're gonna go back to where we kind of skipped out on the previous slide. Right, so we're now going to kind of finish up talking a little bit about, again, some values in units, and also really how to do dimensional analysis and problem solving. We saw a table similar to this, I think, earlier on, and a reminder that you do need to know a majority of these on here as you go through your chemistry career. Again, you will come across a lot of them. So I think we talked about it earlier, but just to sort of reiterate, people, again, always sort of use these backwards. And by the way, when you do see like to the power 10 to the 6 or 10 to the 3, you know, this is basically 1 times 10 to the 6, 1 times 10 to the 3, and so forth, really in scientific notation. So remember that, for example, if you have something like kilo, which is 10 to the 3, and you have something like kilograms and grams, what we see here is how much there is in the base unit to one of the prefix units. So as we talked about before, that means in one of the kilograms, there would be 10 to the 3 grams. So once again, that is the proper way to use that, with obviously grams being the base unit here. And if you switch units, it doesn't really matter. You could have 1 kilometer would equal 10 to the 3 meters. So the prefix you could use on any of them. And again, that is the proper way to do it. If we had micro, which is here, that is 10 to the minus 6. So in 1 microgram, there would be 10 to the minus 6 grams. So once again, grams being the base unit. And again, it's very commonly sort of flipped around the opposite way when people do that. Thank you. So again, as we talked about, definitely we will come across kilo a lot in here, centi, milli, and you definitely should be familiar with those. And deci, as you go on in 1A, you'll probably see a lot more of these guys here, mega, micro, and nano. So again, probably a good little table, and again, it should be in your book. You definitely should know these for sure. You will use them as you go out through your chemistry career. Any questions on that there? Okay. So we talked about some of these common equalities. Remember equalities, which does lead into sort of what we're going to be talking about. When we talk about equalities, again, they are really two different values on two different scales, but they do represent the same sort of amount or quantity of a measurement. So if I say I have 1 meter, it's the same as 100 centimeters. And once again, commonly, as I think we saw a little bit earlier, these two guys do come across a lot here as we go through some of these. Definitely liters and milliliters, we do see a lot. So that is definitely something you should know, that equality. They do represent the same amount of volume. And really from any equality, you can write two different types of conversion factors. So for example, we could write 1 liter over 1,000 milliliters, or 1,000 milliliters over 1 liter. So really from any type of equality, as we'll be talking about, you can really come up with two different conversion factors to help you solve a problem using what is referred to as dimensional analysis. And obviously in most cases, you will not use them both, you would just use one. We talked about a relationship here of our cubic centimeters and milliliters, definitely again, something you should know. And we talked about that. And a reminder again, a kilogram's 1,000 grams, 1 gram is 1,000 milligrams. Those are again two mass equalities that you should know, and does come up a lot in this class in chemistry in general. All right. So we're going to kind of skip ahead of those. All right, so let's talk officially about sort of dimensional analysis and writing conversion factors. As I mentioned, a conversion factor really comes from an equality, and you can write it from any type of equality, where one of the quantities is the numerator, the other one's the denominator. And as I mentioned before, you really can write two different conversion factors for any one that you want. The way that we use this is, for example, if we had two conversion factors where you had unit A over unit B, or unit B over unit A. And let's just say we were starting with unit A and we wanted to get to unit B. So we would choose a conversion factor where unit A would cancel, and in this case, it would be the one on the right. Once again, although it's not written as a fraction, basically unit A is up on top. So to get rid of it, we go opposite of that, and we put it unit A on the bottom. And unit B would go up on top. Once again, we would multiply everything that's on the top. We would then come back through and divide by whatever is on the bottom if necessary. And in this particular case, unit A would cancel. That would leave you unit B. So the reason why the units cancel, you know, if you took unit A over unit A, basically equals 1. The same idea if you took 4 divided by 4, it equals 1, or 2 divided by 2, it equals 1. If you have the same unit up on top and same unit on the bottom, they cancel each other out and they basically equal 1. This sort of way that we show this is what is referred to as dimensional analysis. And this is the way that they want you to show your calculations in chemistry. So they expect you to learn how to properly do that through this class. And as you get to 1A and 1B, you know how to do this. So I would say probably 95% of the calculations that you do should have a setup like this. You know, if it's not just a straight plug and chug into like a formula type of deal, you should show your work here. So that includes the units, the appropriate conversion factors. Any questions on that there? So again, here's a pretty straightforward sort of equality. Obviously here, $1 equals 100 pennies. Again, there are different units, but they do represent the same amount of money. And from that, you could write, you know, 100 pennies over $1. Or you could have $1 up on top over 100 pennies. So obviously if I had something like $5.5, $5.50, I want to know how many pennies that would be. I could use my conversion factor here. Dollars are up on top, which means I want to go opposite here, obviously. And we would have 100 pennies up on top, $1 on the bottom. The dollars would cancel. Once again, here I'm going to take 550 and times it by 100, which is up on top. And that gives me 550 pennies as my answer. So again, you want to get into the habit of showing your calculations like this, using dimensional analysis to do so. Here are some common equalities, and you should be familiar with some of these here for sure. And remember that when we talked about units, there really was two different types of units. There was sort of the English unit or the US unit, and there really was the sort of the metric unit. And there's also some sort of crossovers that we have between metric and US. So in this case, there's a couple of things that we want to sort of consider when we're thinking about calculations and significant figures. So when you set up sort of dimensional analysis, pretty much all you're going to be doing is multiplying and dividing. Is pretty much when you set up a problem through dimensional analysis. And when we multiply and divide, right, we want to look at significant figures in terms of the one that has the smallest for our answer. So if you remember, we talked about certain things that are considered exact numbers. And one of the things that are sort of considered as exact numbers are things that are definitions. So definitions, which are exact numbers, can have multiple amounts of significant figures. So we typically ignore those when we do calculations. Now, when we take anything that's sort of a English to English conversion, it 100% is an exact number, so you don't have to worry about the sig figs of the conversion factor. When we do a metric to metric conversion, you don't need to worry about the significant figures in those conversion factors because they are exact numbers. It is only really, you got to kind of be aware of it here when you cross over. So if you're using some type of conversion factor that is a combination of sort of a metric to English sort of conversion factor, you should look at the significant figures in the conversion factor. Now, there were a few, I think, on a slide earlier on that we saw that were with the exact number sort of slide that has some conversions on there, like this guy that, 1 inch is exactly 2.54 centimeters. So that's still going to be considered an exact number. They want you in here to use not really this conversion. They want you to use the one we just saw, which is a pound is 453.6 grams. So they sort of consider that an exact number as well, so you don't have to worry about it. But let's just say, for example, we use a conversion factor like this, an equality. And from that equality, 1 quart is 946 milliliters. You could write two conversion factors. You could write 1 quart over 946 milliliters, or 946 milliliters over 1 quart. So if you were to use either of those conversion factors in an actual calculation, you should really look at the significant figures that you see in the conversion factor. Now, when you do use sort of a metric to US conversion factor, there will always be one part of it that is a 1. So that is not the numbers you should look at. You should look at the non-1 number when consider it. So if we use this sort of conversion factor, we would consider it to have 3 significant figures based off the 946. And again, in most of those, you would not look at the 1 part of the conversion factor, but the other number in terms of it. I will say probably in 9 times out of 10, though, even if you do have sort of an English to metric conversion, a lot of times the original number that you started with is usually pretty close to the right number of significant figures. Not 100% time, but a lot of times, yeah.
you expect us to advise?
Yeah, so as we talked about before, they want you to kind of know these things as you continue on. So yeah, you should pretty much know most of what's on here, I would say, definitely. And again, it's just some things as we talked about at the beginning, you know, kind of like they don't want you to have anything, they want you to kind of commit these things to memory and stuff. So that's sort of their role here. Yeah. So you definitely need to give, I would say, most of what's on here, definitely. I would say, you know, in this little box for sure, probably this box, and then these metric ones are really kind of like the prefix stuff that we were just talking about, a lot of those. So, you know, those you need to know. And then definitely this one as well. And then some of it hopefully should be common knowledge, like, you know, how many ounces are in a pound, or, you know, by the way, there's how many seconds in a minute? There's not a trick question. There's how many seconds in a minute? 60. There you go. How many? Maybe it is a trick question. I'm not sure, but how many minutes in an hour? 60. How many hours in a day? Only 24. People like to put 60 on that. They like do 60, and like 60 hours in a day. I don't know why. So those are some common knowledge things that definitely will not be provided to you. Although I have had people on test, right? Like, I don't know how to do this. You didn't tell me how many seconds were in a minute. So there hopefully should be some common knowledge hopefully going in. So when we talk about sort of using these equalities and stuff like that, again, really just got to be watchful of that kind of metric to US conversion factor. You do want to not overlook the significant figures in there when you're doing a calculation. You do want to kind of keep them in check. As long as it's not a metric to English conversion that's considered an exact one, like the 1 inch is 2.54 centimeters. So again, this is an equality, and these are the two conversion factors that we could write. Once again, you would not use both of them. So, you know, if we traveled, you know, 55 miles and we want to know how many feet that would be, once again, we would start with what was given to us. We would use the conversion factor where the units are in the opposite location, which would be this one. And we would do 5280 feet up on top, 1 mile on the bottom. Once again, miles on top and miles on the bottom will cancel each other out. And we're just going to multiply here and technically divide by the bottom, although it's 1, so you don't really need to do it. So that is 55 times 5280. We get a big old number there, 290,400 feet. Now, in terms of significant figures, when we look at this, because this is a conversion factor, we don't have to worry about the sig figs that are here. So we would come back to here to look at the sig figs, and this has 2 sig figs, which means we should take it to here. And once again, we do not want to do any kind of super rounding here. So we could leave it as 290,000 feet, or we could do 2.9 times 10 to 1, 2, 3, 4, 5 feet. Again, both would have 2 significant figures in this particular case. Question on that. So a good majority, if you want all the points as we go through these type of problems, you do need to show the work down here. And again, that's what's referred to as dimensional analysis, showing things with the units and the setup like that. Any questions on that? So we were driving 65 miles per hour. So what that really means is, right, in 1 hour, you could go 65 miles. Or if you went 65 miles, it took you an hour to do so. Now, sometimes we do have conversions where maybe we want to kind of convert both units. We got units on top, units up on the bottom. So we can change these things. So for example, we want to know how many feet per minute that was. So we started with 65 miles per hour and we want to do some feet per minute. We want to think about some conversions that will allow us to convert 2 units. So we're starting with 65 miles per hour. And it's basically 1 hour. So up on top, we need to change miles to feet. And we just saw a conversion that would allow us to do that. 1 mile is 5,280 feet. And we also need to convert the bottom from hours to minutes. And as we just talked about, 1 hour is 60 minutes. So if we wanted to write two conversion factors for each of those, 1 mile over 5,280 feet, are 5,280 feet over 1 mile, and 1 hour over 60 minutes are 60 minutes over 1 hour. So these are our conversion factors that we can use. So setting things up in dimensional analysis and setting the units up like this is really fractions, allows you to keep track of things and do the correct math. Sometimes when people don't do sort of dimensional analysis and they kind of do just like numbers under numbers, they're not sure if they should be multiplying or dividing, and they usually will get things wrong. So for example, here, I want to get rid of miles. Miles are up on top, so I want to get rid of it. We're going to go opposite and put miles on the bottom. So that would be 1 mile is 5,280 feet. If I stopped right at this point, the miles up on top and the miles on the bottom would cancel. And the units I would be left with at this point are what units? Up on top would be feet per hour, right? So that's pretty close to what I want. I got my feet done. Now I need to change the hours on the bottom to minutes. So this is important. Did you set it up this way? You can clearly see that the hours are on the bottom, which means to get rid of hours, you actually need hours up on top. So that would be the conversion that we would want to use. And we would do 1 hour up on top, 60 minutes on the bottom. The hours would cancel. Now the units I have on top are feet. The units I have on the bottom are minutes, which is exactly what I'm looking for. Now, in this case, because I set it up this way, I know that I'm going to basically multiply across the top. So everything here is going to be multiplied. And then I'm going to come back and divide by whatever's on the bottom. So in this case, what I would do is take 65 times 5,280 times 1, basically hit equals, divide it by 60, and I will end up with, it looks like 5720. The units here, once again, are feet per 1 minute. So the number stays with the top unit, and it's always 1 on the bottom. Significant figure-wise, what should my sig figs be? This is a exact number, which means that we don't need to worry about it. This is also an exact number, which means we don't need to worry about it, which once again means we should come back here to our original number, which was 2. And our answer actually should have 2 significant figures in this case. So it really should end up at 5,700 feet per minute. Any questions on that there? So the way I set it up there, again, is dimensional analysis. That is the way you need to set things up. You got to show the setup like that and the units. I will also say that sometimes people run into trouble with their calculator because they want to punch everything in at once. Very bad idea. So I would highly recommend that you do it this way, that you don't get the wrong answer. You can multiply as many numbers as you want across the top. So as many numbers as you got up there, you can just keep multiplying them. You do want to hit equals at the end. Then come back and divide by the first number on the bottom, hit equals, divide by the next number on the bottom, hit equals, or however many numbers you got on the bottom, just keep doing that. When people try to put all the numbers in and then divide by all the numbers on the bottom, if you don't put parentheses correct, your calculator will do the math wrong and you will get the wrong number. What's your question? It is. So it's based on the same ideas I think we might have talked about before, but the idea is in any type of calculation, really your calculation is only as good as your worst measurement. So the one with the least number of sig figs or the least number of decimal places are technically like your worst sort of values. So your numbers is only as good as that. It's kind of like the weakest link. So you're only as good as the weakest link. So in a calculation, the one with the least is sort of like the weakest link and is as good as your calculation really could be. If they all went to a bunch of significant figures, each of them, your answer would then go to a bunch of significant figures. And then, you know, you would be pretty, you know, out there in terms of your value and stuff like that. Other questions? Okay. Okay, so obviously we could pull conversion factors sometimes in the problem. So maybe in the problem it says you got some 91 octane. Clearly you can see how old this slide was. That was a lot of money back then, 305. I would kill for some 305 gas right about now. But so if you got 1 gallon of gas, it would cost you $3.05, or $3.05 is equal to 1 gallon of gas. So sometimes conversion factors can be found in the actual problem. You need to kind of pull them out. And for the most part, if it is a conversion factor that you pull out from the problem, you probably should look at the sig fig. So if we were to use this, you probably should look at the significant figures, because not every gallon of gas costs $3.05. So it's really more of a specific one. And you should probably look at the significant figures here. Also, kind of like the density problem that we did earlier, you know, sometimes we may be given a value like we were with that density value, and we can convert them into usable conversion factors. And in this particular case, we did look at the significant numbers that were in here, again, because not everything has a density of 2.16, right? So it's not really an exact number, it's really more specific and stuff like that. So sometimes we will pull these conversion factors out of the problem. You should look at the significant figures that you see there. Now, sometimes we are given percentages, and as you may know, one of the easiest way to sort of turn a percentage into a usable number is to assume 100 of something. So if we have 12% body fat by mass, that means we have 12 kilograms over 100 kilograms of body mass. Or if you want to do more of a English one, we have 12 pounds over 100 pounds of body mass. So really, if you're given anything that's a percentage, the easiest thing is just to assume 100, kind of convert it into 100. If you had, you know, something that was 5% by mass, and that's what that means, mass to mass, M to M. You could just say that was sodium chloride solution, for example. You could say there would be 5 grams of sodium chloride and 100 grams of solution. Or you could flip it around and go in 100 grams of solution, there would be 5 grams of sodium chloride. So it's a very common thing that we come across in chemistry is we're given numbers sometimes as percentages. We want to kind of use them as usable sort of values. So we do convert them by assuming 100. You really could assume as much as you want, but the numbers change. So it's just easier to assume 100 rather than assume 200, where you have to make it 10 and so forth. Any questions on that? All right. So as I mentioned, what we've been talking about here and what I've been showing examples of are as was referred to as dimensional analysis. And again, that's really showing the units, allowing the units to cancel out using the correct conversion factors. So there are several steps that you want to kind of go through when you do these type of problems. A lot of times it's helpful to write what's given to you in the actual problem. It's also helpful to write what you're looking to find. You want to think about what equalities will get you there. By the way, with conversions, you know, there could be different paths to get you to the answer, depending on what conversions that you use. So they may not be wrong if you sort of chose a different path, as long as there's a legitimate conversion factor. From the equalities, you want to write the proper conversion factors. Most importantly, for credit in this class, these are really the two things that you got to for sure show. You need to set up the problem where you show the units canceling with the conversion factors like I demonstrated in the last couple examples. You also need to obviously solve the problem to the proper number of significant figures with the proper units when it's all said and done. So let us try some here, maybe. We'll skip this one. Kind of did that. All right, let's try this one. You go to the local AM/PM, you get 32 fluid ounces of Diet Coke from the Thirst Oasis. How many gallons of Diet Coke did you drink? Here's a couple of equalities that might be helpful for you and some conversion factors that go with it. All right, so set up the problem using dimensional analysis and get yourself an answer. Let's take a minute or two and see what you come up with. Okay, let's take a look. So again, we are starting with 32 fluid ounces. We want to get to gallons. So that's definitely where we want to start, which is 32 fluid ounces. Once again, we want to get rid of fluid ounces. It's up on top. So we will want to use the conversion factor here to do so, to take us to quarts. So on the bottom here, we get 32 fluid ounces. Up on top is a quart. If I stopped right at this point, the fluid ounces in terms of the units would cancel. The importance of setting up like this is we have quarts up on top. So now we know to get rid of quarts, we need to put quarts on the bottom. So we would then use the conversion factor there on the right to do that. Opposites cancel. So we're going to, on the bottom there, go with 4 quarts and 1 gallon. Quarts up on top, we'll divide out the quarts on the bottom. Once again, we're going to multiply everything up on top. We're then going to come back and divide by what's on the bottom. So here, basically, we're going to take 32 divided by 32 and then divided by 4 will get us 0.25 gallons. First off, question on the calculation here. Now, in terms of significant figures, we pretty much got a conversion factor that's an exact number. So once again, here we're going to come back to that original number, and has 2 significant figures. Again, with dimensional analysis, you're pretty much only doing multiplying and dividing. So it's always going to be sig figs that you want to look for, and the smallest, which would give us here. The answer is 0.25. The answer is not 1/4, because that makes me think you're just too lazy to divide. Yeah. So never leave an answer as a fraction. Yeah. Not for that bad example there, but I have had people write things like, 445 miles over 1,020 hours and circle it. So never leave an answer as a fraction. Divide it out, get a number to the proper number of sig figs. Question on that one there. I will say that for the most part, the department wants you to do these conversions with dimensional analysis all kind of in one move, all in one sort of calculation. So as you go on, they may expect you to do that. Personally, I don't really care if you do it individually, like, do the first part, get a number, do the next part, get a number, and so forth, as long as you show all the conversions. But as you go on, some instructors want you to make sure you just kind of do it all in one move. I will say, though, if you sort of do it in piecework, again, try not to round to the very end. So if you kind of get an answer and round and then take it, get another answer round and do another conversion, again, you'll be moving yourself farther and farther away from the right answer. So just avoid rounding if you kind of do it in piecework. But I will say they kind of want you to do it all in kind of one step, if you will, or one sort of calculation. Any questions on that? All right, let's try another one here. You got an antibiotic dose, that's 500 milligrams. If it comes in 250 milligrams in 5 milliliters, how many milliliters would be given here? Okay, let's take a look. So in this particular case, we have 500 milligrams that we want to give to somebody. The medicine comes in 250 milligrams per 5 milliliters. So this is a case where, again, we're really going to kind of get a conversion factor from the actual problem. And because we could kind of use it as a conversion factor, we could write really the 2 different forms of it. When we approach it the same way, we're going to start with our 500 milligrams, which I guess should have a dot right there. So we'll go with our 500 milligrams. Once again, using dimensional analysis, we can see the milligrams are up on top. So to get rid of it, we do need the milligrams to go on the bottom. So we want to use that as a conversion factor opposite. This is going to be 5 milliliters up on top and 250 milligrams on the bottom. Once again, here, the milligrams will cancel each other out. We will multiply the 500 times the 5, and then again, come back and divide by the 250 here. So we're going to take 500 times 5 divided by 250, gonna give us 10 milliliters. First off, any question on the setup here, the problem? Now, significant figure-wise, what should we end up at? We really should end up at 2. Once again, we really should look here at this guy. It's not an exact sort of conversion, right? It's specific for this problem. So really, they're both hanging out with 2 sig figs. Our original number had the decimal point at the end, which was 3 sig figs. So in this case, we should have 2 sig figs, which means I probably need to put a decimal point there. If I didn't put the decimal point there, I would only have 1 sig fig. You also could do a little scientific notation as well, if you want, which would be 2 significant figures. Yeah. No, so again, you kind of have to know some of those ones we talked about. So here they're just showing you to show you what you could do with them. So for the for points on the exam, if that's maybe also a question, the thing that you 100% need to show is really just this part here. Yeah. If it helps you to do find and what was given and all the conversion factors, you could do so, but you don't necessarily have to do it for quiz or exam, but you do need to show what's in the box, basically the setup with the conversion factors being used, the units canceling out, and the final answer with the proper sig figs and units. Any questions on that? Yeah. But again, if it helps you with the other, go for it. All right, so again, here's some equalities and some conversion factors that may be helpful for you. During surgery, 5 pints of plasma, how many milliliters of plasma are given? And once again, here we got 5 pints. We want to eventually end up in milliliters, so we definitely want to start with what was given. We got our 5 pints. So using the path here, we want to go opposite. So we're going to put pints on the bottom, which would give us 2 pints is 1 quart. At this point, the pints would cancel. If I stop right here, I would be in units of quarts, which is close to what I want, but I do want to get to milliliters. So using this equality and the proper conversion factor here, which would be this guy here, we will put quarts on the bottom so that they cancel. And that will leave us milliliters up on top, which is what we're looking for. And again, here the quarts would cancel. Again, multiplying across the top there, 5 times 946. We're going to hit equals. We're going to divide it by 2, gets us 2365 milliliters. Now, in terms of sig figs, we do want to look here as it's kind of a English to metric sort of conversion there. That's 3 sig figs. We don't have to worry about this guy. And this guy here has 2 sig figs, which means we should actually end up with 2 sig figs, which you could write as 2400 milliliters. Or if you want to do scientific notation, 2.4 times 10 to the 3 milliliters. So either one of those would work. Yeah. Like it. No, you don't have to. So again, you just need to show this setup with the answer. And just make sure you punch it into your calculator correctly. Yeah. Other questions? Okay. So again, as to the earlier question, quizzes, exams, this will be the problem. And then you'll have this answer and you may not be given, obviously, the conversion factor. So, okay. One last one here to make sure. We're stranded 125 miles away from home. You decide, why not? Let's walk it. Rates to, you can use it to convert from a distance to a time. We're going to do that, but we do have an issue here in terms of units. We have one that's in miles. We have one that's in feet, so we cannot use them the way they are. We either have to convert the miles to the feet or the feet to the miles so that everything will cancel out correctly. I personally am going to convert the miles to the feet. So if I do 125 miles using a conversion factor that comes from this equality, we want miles on the bottom so that they cancel, and feet up on top, 5280 feet. Miles will cancel. 125 times 5280 gives us like 660,000 feet. Definitely got your steps in for that day here, feet. So now that we have it in feet, obviously we can now use really the rate the way it was given to us so that they would cancel. Once again, we could use that rate as a conversion factor. We could say 55 feet per minute, or we could flip it around and use minutes up on top and 55 feet on the bottom. So we're going to go 660,000 feet. To get rid of feet, we're going to use it in this version here. Minutes is 55 feet. I guess 0.0 would be good to put there. There we go. The feet will cancel. At this point, the feet are gone and we're in units of minutes, which is good because we do want to end up in time, but we don't have the right unit of time. We have minutes. So once again, minutes are up on top. So to get rid of minutes, we're going to go opposite. So there are 60 minutes in 1 hour. Minutes will cancel. If we stop right here, we're in units of hours, but we do want days. So we're going to go hours on the bottom to get rid of it, which again is 24 hours in 1 day. Hours will cancel, and now we are left with days. So we're basically going to take 660,000, and they're pretty much all one up on top. We're going to divide it by 55, divided by 60, and divided by 24. And we get something like 8.333, a whole bunch of 3 days. First off, any question on the setup here? Yeah. You can get to the same answer if you use some different conversions. It depends what conversions you use, yeah. But they all should pretty much give you the same answer. And it's all good as long as, again, you show the setup and they're legit conversions, not ones you made up. Yeah. Yeah, so there's different ways to do it. As long as you get to the same answer and you show the setup, it's okay. Again, you could also, if you wanted to, just convert the feet per minute into miles per minute and use it that way. So there's, multiple sort of ways, but they all should, again, get you kind of the same answer at the end. And you do need an answer like this, not like you'll make it there in so many days, approximately this many days, so you do need to make sure you get the right sort of answer. In terms of sig figs, this is an exact number. This is an exact number. We should look at this one, which, if I wrote it correctly, does have 3 significant figures. Although this one written like this has 2, the original number had 3 as well, which means technically we should end up with 3 significant figures here as our answer. Just a nice leisurely 8.33 day walk. Yeah. Any questions on that? Yeah. It's all good as long as you showed for me, I'll say for me, it's all good. Okay, as you go on, it might not be, they may want you to do it all in one step. If you did this and got an answer, and then did this and got an answer, did this and got an answer. It's all fine as long as you showed in each of the steps the conversion factor and the units canceling. It's okay. Just don't round too much until the end. Other questions on that? Now, I will say you do want to show it like this with the dimensional analysis. I can't tell you how many people will do this problem and frankly multiply these guys instead of dividing. Yeah, so if you keep it all in the right way without just kind of stacking all the calculations, you will hopefully be able to visually see, oh, I should be multiplying here, I should be dividing here. It's a super common error. People will start multiplying those because they really have no idea where the time unit is on top, is on the bottom. So it's a really benefit to make sure you do it that way. Question on that. Question on dimensional analysis, conversions, equalities, conversion factors. Yeah. 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 So for example, these are pretty much all, basically the same sort of conversion factor. So if we go back to, let's see, where's that table there? Somewhere there, coming up, I think. So now if you're pulling anything that really comes from sort of this column, if you will, or anything that's really an English to English, you don't have to worry about the sig figs because they're considered exact numbers. If you pull anything from sort of a metric to metric sort of equality, you don't have to worry about the significant figures because they're also considered exact numbers. It's really only when you get to sort of this column here, and obviously they're not all on here, obviously, but you do need to kind of look at them. There are some exceptions, like this one you don't need to look at because it's considered an exact. This school uses this one as considered sort of an exact, so you wouldn't have to look at it. But like the one we talked about here where we had, this sort of thing here, you should look at it. And whenever you have sort of an equality like that, that is sort of English to metric that you need to look at, there will always be one number that will be one of the units will be one. So you don't have to worry about that because it's just one. You want to look at the other number. So here we would look at the 946 if we were using this in a calculation and go, okay, it has 3 sig figs. Is that more or less than, say, some other number that's there? And that's how you would do it. For example, if you pulled this one, you wouldn't look at the 1, but you would look at the 1.06. And I will say probably in most cases, and again, not 100% of the cases, but in most cases, probably still your original value that you're converting is probably the one that you should look at, and probably nine times out of 10. It was not perfect, but if you want a sort of a non-perfect thing, but probably right in most cases, go with the original number. Is usually pretty close to what it should be. But that's how you would do it in a sort of a metric to US sort of conversion. You want to look at the actual one that's a number, not the one that's a 1. Yeah, I say this chart's probably a good one. It probably has a majority of the ones that they kind of want you to know. Again, if it's something like on a quiz or exam that I feel like maybe you wouldn't know, or maybe we didn't talk about it, I probably would give it to you. But in most cases, like I said earlier, they really don't want us giving very much and stuff like that. So this is probably a fairly good table. You have probably a similar one in your book. There's a lot of things that commonly come up sort of in chemistry classes. Other questions? Now, if we had something, say, let's say we had something like let's say we had 1,245 cubic inches, and we want to know how many cubic feet that would be. Why don't you do that conversion and see what you come up with? Again, 12 inches is 1 foot. Yeah. Okay, so since we're getting to the end here, let's take a look. So this is 1,245 cubic inches. I again want to really use my equality here just like normal. So we want to get rid of inches. So 12 inches is 1 foot. Does that actually get rid of all of it? It doesn't, right? Because this is cubic feet. You technically need to do it not once, not twice, but you technically need to do it 3 times in this case. This way, inch, inch, and inch, that is cubic inches, which cancels them all out. When we now multiply, that's feet times feet times feet, which is cubic feet. And we do get the right number here, hopefully. That would then be 1245, basically divided by 12, divided by 12, and divided by 12. Gets us 0.7205 cubic feet. Exact number, exact number, exact number, 4 sig figs, 4 sig figs here in terms of our answer. Now, it's really common that sometimes people go, well, can I just do this? And the answer is, yeah, you can, but make sure you actually do it 3 times, because most people don't. Most people just do it once and go, well, I wrote it, so it looks pretty good. So sometimes it's better just to write it out so you remember you should really do it 3 times. If not, make sure you do it 3 times. So that's a very common mistake sometimes people will make as well. Any questions on that there? Questions on conversion factors, dimensional analysis, any of those things? All right, so that pretty much wraps up chapter 2. There's a few slides at the end about specific gravity. We're not going to talk about